Hello, we're going to talk about wound rotor motor starting circuits. Here's a wound rotor motor that's from one of the local sawmills. We can see the incoming feeders to the rotor circuit, single conductor wires, and on the other side are the three single conductor feeding the power circuit. Okay, the most basic control for our wound rotor motor. This gives us 3 stages of starting. So we've got our incoming power L1, L2, L3. We've got our M contacts. We've got 2 other sets of contacts, 1A and 2A. And with 2A and 1A off, we've got full resistance in the secondary circuit. When 1A energizes, we're shorting out set 1. Then when 2A energizes, we're shorting out set 2, and we're running with no resistance. So as we remember from wound rotor motor theory, the best starting torque and the lowest current is going to happen with the full resistance in the circuit. So if we look at this starting circuit, we hit the start button, we energize M, that energizes the motor with 3-phase power, seals itself in. This normally open time closed M contact is from a timing module that is part of the M contactor, just as this 1A normally open time closed contact is a contact from a timing module on the 1A contactor. So when M energizes, the timing module starts to time out, and that will close this contact. But without 1A closed, we get full resistance, the motor starts to accelerate, and as the motor starts to accelerate, the torque will start to decrease until it will set in at a certain slip speed. Hopefully our timer is set correctly. At that point, this contact closes, which shorts out set 1. The motor will then accelerate until the acceleration slows down when the power factor of that rotor gets to about 70%. And then hopefully at that point, this time delay is set to energize contactor 2A, and 2A will short out the secondary totally, and the motor will do its final acceleration. And 2A seals itself in, and at the same time disconnects 1A. So the motor is now running at its full speed. Okay, the only disadvantage to this circuit is it will not work well with a variable load on the motor. If the load is very high or at 100%, these times are fixed, so the transitions between speeds might not be at the optimal point of the torque curve. So this second circuit is very similar, where we've just got a start-stop circuit. There is no timers, but we've got the 1A and the 2A contactors, but notice they're using normally closed contacts. So with 1A de-energized, these contacts are closed. With 2A de-energized, these contacts are closed. So the theory behind this circuit is when we initially start the motor, the rotor frequency is at its highest, and E-gen is at its highest, because we're cutting the rotating magnetic field of the stator is cutting the rotor wires or the rotor windings at the fastest rate, giving us the highest voltage. So the voltage will be applied to these contactors and they will both pull in. So these will open and we're applying full voltage to the starter. Now we've got 2 very similar contactors. The coils of these contactors are going to be very similar, but we've got a capacitor in series with 1A. So we know a capacitor connected to AC, its inductive reactance is inversely proportional to the frequency. So when the frequency is high, the impedance of the capacitor is very low, or it's going to allow the current to pass through easily. But as the impedance drops, as the frequency of the rotor drops, the impedance of the capacitor is going to increase. So as the impedance of the 1A circuit is going to be different at different frequencies than 2A, and that will cause the impedance to be high enough to not supply enough current to hold 1A in. So at some point, depending on the value of capacitance and depending on the impedance of 1A will drop out before 2A. So when 1A drops out, we're eliminating these resistors and the motor will accelerate. The beauty of this circuit is that should happen at the same speed no matter what the load is. So we're going to accelerate to the same RPM before this drops out. Remember, this would have to be calibrated. Then when the frequency drops to a low enough value and the E-gen drops to a low enough value, we'll not have enough current for 2A to hold in. 2A will drop out and these will close again. That will short out the secondary and we will accelerate to our final speed based on the load. So this is an interesting circuit because it will change its timing depending on the load. The more load, the longer it might take to drop these relays out. Okay, on this circuit, this is just a reversing circuit. So we have a very similar circuit to the first circuit, except now we've got a reversing contactor. So this is no different than any other reversing circuit, but the timing of the contacts just work whether it's going forward or reverse. And remember, we're changing direction of a wound rotor motor by just changing the phase rotation of the incoming supply. Changing the secondary connections has no effect on the rotation. These drawings, by the way, are on Learning Hub, so you can review those on your own. And the final drawing is, this is the lab that we have in the third year, or the starter we have in the third year lab, where we've got a selector switch where we can leave the resistance in, or we can add resistance or remove resistance. So essentially, we've got a 50% speed, 75% speed, and 100% speed. When we're at 50% speed, we have all the resistance in the rotor circuit. And when that happens, our slip is going to be at its greatest, but our speed regulation is going to be very poor. This will be a very crude form of speed control. Not something you're likely to see anymore, but if we can understand the theory of the wound rotor motor, we can understand this circuit. We're going to have the highest percentage of slip, and we could say with all the resistance, the slip is going to be 50%, so we're going to have 50% of normal speed. And notice when it's in the 50% position, that's disabling the circuits that are controlling S1 and S2. When we put it in the 75% spot, we're using T1, and after T1 times out, it closes this contact and S1 closes, shorting out this section of resistors. Now the slip speed will decrease and hopefully to about 75% of normal speed. That would be based on what value of resistors we had here. That would have to be closely calibrated to those desired speeds. Then when we put it in the 100% spot, now we are energizing CR, which closes this contact. It's going to go through the starting sequence because this is where we would have it if we were starting it from a dead stop and wanted to go to full speed. It still has to go through the same starting sequence. So T1 will start timing out. Then after it times out, S1 will close, which will, so S1 will close, and when CR is closed and S1 is closed. T2 starts to time out. When it times out, T2 closes here, energizes S2, which bypasses all the rotor resistance. Then we get to full speed at that point. So again, 50% speed, 50% slip, 75% speed, or 25% slip, 100% speed, probably 3, 4, 5% slip. I just want to clarify the automatic frequency sensing starting of the wound rotor motor, where we're using our two contactors, 1A and 2A. So this will accelerate the motor more consistently with a varying load. So it's always going to drop the resistance out at a specific speed or close to a specific speed rather than time. So this would be a more accurate way of starting that motor. So with these two contactors, if we can think of a capacitor in series with the coil and connected to the rotor, basically the rotor voltage, and remember, from 0 speed to full speed, the frequency of the rotor goes from 60 hertz to 0 hertz, or we go from 100% slip to 0% slip. So as the speed of the motor increases, the E-gen in the rotor decreases, but the impedance of this coil with the capacitor actually increases as the motor speeds up. That's because we're familiar with this formula. Capacitor reactance is equal to 1 over 2 pi Fc, or Xc is inversely proportional to frequency. So as the frequency drops, Xc goes up. So if the impedance goes up, the current through the coil goes down. So it's going to get the current through the coil. Remember, the current through the coil is what's pulling that coil in. So we're going to get to a certain speed based on the value of the capacitance and the impedance of the coil, where we're not going to get enough current to hold that coil in. Then it will drop out. And remember, we're using normally closed contacts. The contacts will close and short out the first stage of resistance. So this is just a chart to understand, as the impedance of the coil goes up because the frequency is going down, because we have to remember this, the current through the coil is dropping until it hits the critical point of not having enough flux to hold that coil in. The coil drops out. And at the same time, E-gen is also dropping because it's proportional to the relative speed between the rotating magnetic field and the rotor. And as the speed of the rotor increases, the E-gen is going to decrease as well.